Hi, my name is Danielle McNeese. I'm a mechanical engineering master's student here at Texas Tech University, and today I'm going to be talking to you about wind farm layouts and their optimization methods. First, I want to give you a presentation overview. I will give a brief introduction, then go into a literature review where I will discuss four major topics: the history of wind farm layouts, failure modes of individual turbines and their effect on the farm as a whole, turbine siting, and optimization tactics. Next, I will discuss the new concept in optimization versus the older concepts. Then I'll wrap it up and show you the sources I used for the project. So why is this an important topic in wind energy? If wind turbines are placed correctly on a farm, one can improve the performance and efficiency of the farm. The cost of energy and many other expenses could potentially decrease as well. Lastly, the net energy output can be maximized to compete with other sources of energy. So let's move into some research about how wind farms have evolved. NASA and the U.S. government worked in the 1970s and 80s to create a utility-scale wind turbine industry. After the National Science Foundation funded the project, 13 turbines were constructed from 4 different turbine designs. Could this be considered the first wind farm? The Department of Energy claims that wind energy has been around since early recorded history. However, the first large-scale wind farms weren't installed until 1980 in California. Through this venture, many lessons were learned. Among these lessons were proper siting and the impacts to the environment and surrounding communities. This also led to a change in overall turbine design to achieve a lower influence to external parties. This is where we see the first optimization problems beginning to arise. Now I will discuss the issues associated with turbine failures and how they affect the farm as a whole. So what could cause a turbine to fail? There are many reasons. An insurance company named G-Cube analyzed the top 10 causes for turbine failure on their website, which include gearbox issues, fire, lightning strikes affecting the electrical systems, blade issues, mechanical breakdown, human error, which is often the case, yaw motor events, and poor operating and maintenance arrangements. If any of these events occur, it could potentially affect the farm depending on the size. Shrapnel from a blade breaking could damage a nearby turbine, and that could hit a nearby turbine, and so on. The placement of turbines is based on a wind speed and direction and calculated based on interferences from the surrounding turbines. If that turbine is gone, it will change how the controls of all the surrounding turbines respond. Most importantly, any downtime of any one turbine could decrease the net energy output of the wind farm, which means lost money. The class textbook by Manuel defines turbine siting as determining the most appropriate locations for multiple wind turbine installation. The Manuel book again defines 5 stages for large-scale siting, which are identifying geographic areas that need further investigation, selection of candidate sites, initial candidate site evaluation, final site evaluation, and micrositing. Micrositing is the process of choosing the exact location of the turbines and determining their energy production capabilities. The major initial challenges when siting a potential farm include finding a cost-effective grid connection, preferably a medium voltage grid for the desired size of the farm, ensuring there is adequate wind, maintaining cost-effective construction efforts and site access, obtaining the appropriate permits to build a wind farm in this location, and securing the land rights. When looking into a potential site, some general strategies are followed in industry. Initially, an area needs to have good exposure and low vegetation. Any hills need to be smooth with little slopes, as this can cause separation of flow. The area needs to be accessible, as complexity of the landscape can increase the cost. Lastly, the land needs to be available with few landowners. When an engineer begins to plan a wind farm for optimization, 3 major parameters are required. These parameters are the type of turbine to be installed, the number of wind turbines to be installed or the desired power output, and the distribution of wind speed and direction over time. The first goal of optimization is to minimize the deficiencies due to wake effects or the shading effect of a wind turbine on the other turbines downstream from it. An article in the journal called Renewable Energy by Gonzalez et al. Entitled Optimization of Wind Farm Turbines Layout Using an Evolutive Algorithm explains that when two turbines are placed too close to each other in the dominant wind direction, the total amount of generated power is less than the initially expected individual power sum because the wind power in the airstream available for the downwind turbine is now reduced by the upwind turbine. Utilizing farm layout planning and analyzing wake models that quantify the growth of the wake and velocity deficit as a function of distance can alleviate these effects. Therefore, it is a balancing act between installing the turbines as close as possible to increase the surface density and avoiding turbine interference by the wake from upstream turbines. Also, the engineer needs to continuously minimize the cost of energy while maximizing the net energy production by optimizing the farm layout to avoid these inefficiencies due to wake effects. Looking at the original research done on wind turbines and the inefficient farms compared to recent farms, one can see that the older methodologies made very limited assumptions regarding the wind variations when estimating energy production. They also quickly began to realize that there is an optimal number of turbines that can be utilized in a certain area of land. This is caused by the shading effects from turbines upstream, and the overall effect is a decrease in farm efficiency, making the energy production calculations incorrect. Due to the complexity and inability to describe this problem in analytical form, classic analytical optimization techniques cannot be used to position turbines. New optimization methodologies include a variety of evolutionary algorithms and unrestricted wind farm layout optimization, or UWFLO. A 2013 study by Chowdhury et al. Advanced the UWFLO method by avoiding the traditional assumptions made and utilizing a mixed discrete particle swarm optimization algorithm. It was applied to a 25-turbine wind farm in North Dakota, and a 6.4% improvement in the farm capacity factor was noted by simultaneously optimizing the turbine selection and farm layout. This same research team developed a response surface-based wind farm cost model to constrain the cost of energy of the desired farm. Evolutionary algorithms as an optimization tool for the wind farm layout design problem have recently proven to be sufficient and effective. In Gonzalez et al. Of 2010, a global wind farm cost model using the initial investment and the present value of the yearly net cash flow was proposed. Taking into account wake decay effects and differential terrains, the results of this algorithm were favorable in determining a wind farm configuration. Another evolutionary algorithm by Gonzalez in 2011 optimizes the profits given in investment on a wind farm. The difficulty in this problem is due to many attributes. There is no analytical function to model the wind farm costs in determining initial investments, nor an analytical function to model net power generation. Also, this algorithm mixes discrete and continuous variables and includes ranges of non-allowed values in the solutions. Though there has been much progress in the optimization of wind farm layouts, the new methodologies haven't all been successful in developing algorithms to solve the problem. The need for wind energy continues to rise, however, and optimization is absolutely necessary to produce energy in an efficient manner. This is my list of references that I used throughout the project. And with that, I would like to thank you for listening today, and please let me know of any questions.